In this paper, we proposed a novel approach that reconstructs high-fidelity and topology-consistent garment mesh from single-in-the-wild images. High-quality 3D digitalized humans are highly demanded by various real-world applications. However, creating them usually requires tremendous effort from experienced modelers or expensive multi-camera systems. Therefore, we focus on single-image reconstruction, which is more accessible for amateurs and will provide professional modelers with more diversified initialization. Moreover, reconstructed garments should be represented as layered meshes, which will bring better photorealism and benefit further content creation. The main challenges towards a high-fidelity garment reconstruction can be summarized as two folds: generating garment styles and recovering surface details. Unfortunately, the state-of-the-art single-image garment reconstruction methods fall short in generating garment styles and surface details well aligned with the input image. In the last 2 years, the emergence of the pixel-aligned implicit framework, namely PIFU, shed light on reconstructing clothed humans with image-aligned appearances. It also poses a question: how to generate layered garment meshes from full-body implicit fields. To address this problem, we propose REEF, a novel geometry inference framework that can produce high-fidelity layered garments by registering the explicit garment template meshes to the full-body implicit fields predicted from single images. Our method consists of 2 stages: aligning explicit to implicit and fitting explicit to implicit. In implicit alignment stage, we set up the correspondence between the explicit garment templates with an implicit clothed human using implicit boundary fields and the semantic fields predicted from input images. On top of the prepared implicit fields, in the explicit fitting stage, we will deform the explicit garment template to be aligned with the implicit fields. We designed class-specific garment template meshes based on SMPL, which covers 12 common clothes categories. We define the outermost curves of each template mesh as the explicit garment boundaries. We adopt the pixel-aligned implicit framework to generate the target implicit clothed human body. For more details, please refer PIFU and PIFU HD. We propose to set up boundary correspondence between the explicit template mesh and the implicit target for later template deformation, as the boundaries possess the most prominent geometrical features of the garment shape. The garment boundaries are thin curves that are inherently hard to be captured by the implicit functions. Therefore, we propose to model each garment boundary as an implicit cylinder with a signed distance field. To predict the garment boundary fields that align with the implicit clothed body, we firstly design a vanilla approach that regresses the implicit garment boundary from coarse shape embedding in PIFU HD. However, it may not reflect the boundary appearances shown in the input image due to the lack of guidance received from the image space. To address this issue, we propose a novel curve-aligned boundary generation module that receives extra guidance from the 2D boundary attention map. The boundary attention map is generated with higher HRNet and can be supervised with rendered ground truth boundary heat map. Similarly, we can generate the semantic field. In the implicit alignment stage, we have set up the correspondence between the implicit clothed body and explicit template with curve-aligned boundary fields and semantic fields. On top of the correspondence, we can progressively deform the template mesh to align with the implicit surface. A pose initialization is performed by optimizing the SMPL parameters to fit the low-resolution clothed human body and the 2D joint detection. Based on the pose initialization, we can further deform the template boundaries to the implicit boundary fields. By setting the boundary alignment as the hard constraints, we can get a fair surface with accurate boundaries by performing biharmonic deformation. To eliminate the effect from non-relevant areas in the implicit clothed human, we proposed the activate area probing. Vertex on the surface, we cast rays along the normal direction and find the first intersection to the implicit surface. The action status for the vertex is set to active only when the cast rays reach the ISO surface, and the semantic label at the penetration point is consistent with the current template. Only the activated vertices will be updated during the optimization. By iteratively optimizing the vertex position of the template vertices, we will get a high-fidelity garment mesh with image-aligned styles and surface details. As the generated garment meshes are topology consistent, we can easily stitch the collar meshes to the main garment template meshes. Here are the qualitative comparisons between our method and the state-of-the-arts. Here are the results on in-the-wild images from the internet. Thank you for watching.